What if the biggest breakthrough in aviation wasn't about flying higher, but folding something everyone thought could never move? In 2013, Boeing made a quiet decision that would challenge one of the oldest assumptions in aircraft design, that wings are fixed, permanent, untouchable for over a century. Commercial airliners followed a simple rule. If you wanted better efficiency, you built longer wings. And if those wings didn't fit at airports, that was the airport's problem. This time, it wasn't. Airlines were cornered. Fuel costs were rising. Environmental regulations were tightening. Long-haul routes had to stay profitable. They needed an aircraft that could fly farther, burn less fuel, carry more passengers, and somehow still squeeze into gates designed decades ago. There was one catch. The physics didn't cooperate. Longer wings mean better lift. Better lift means lower fuel burn, and lower fuel burn is everything on a 15-hour flight. But airports around the world were built around strict size categories. Go beyond them, and suddenly you're asking hundreds of airports to rebuild taxiways, expand gates, redesign terminals. That's billions of dollars no one wanted to spend. So Boeing faced a contradiction. Build bigger wings and make the plane unusable, or stay within limits and lose the efficiency war to Airbus. They chose a third option, and this is where things start to get uncomfortable. Instead of accepting the limit, Boeing decided to break it. Selectively, they designed a wing so large it stretched 235 feet from tip to tip, wider than anything the company had ever built for a commercial jet. A wing with an ultra-high aspect ratio, carbon fiber composite, curved and sculpted to slice through air with less drag. On paper, it delivered a dramatic jump in aerodynamic efficiency, but on the ground, it didn't fit. So Boeing did something no commercial airliner had ever done before. They made the wingtips fold, not slightly bend, not flex, fold. 11 feet of wing on each side would rotate upward after landing, shrinking the span enough to slide into existing gates. In the air, it would be the most efficient wide-body wing Boeing had ever produced. On the ground, it would pretend to be smaller, elegant, terrifying, because now the question wasn't about aerodynamics, it was about failure. What happens if a wingtip unlocks in flight? What happens if power glitches at 35,000 feet? What happens in crosswinds, under full load, during the worst turbulence imaginable? There were no regulations for this, none. Commercial aviation rules never anticipated folding wings on passenger jets. That meant Boeing wasn't just building a new aircraft, they were forcing regulators to invent new rules around it. The FAA responded with something rare, special conditions. Boeing had to prove that no force in flight, not torque, not vibration, not electrical error could ever unlatch those tips. Every power source capable of triggering the mechanism had to be isolated before takeoff. Worst-case scenarios had to be simulated and survive, and certification didn't go smoothly. Delays stacked up, testing extended. Delivery dates slipped first, 2020, then 2025.
The conditions
now projected for 2027.
Limits
From the outside, it looked like another troubled program. But this only matters once you see what was happening inside the engines, because the folding wing was only half the gamble. To make the numbers work, Boeing needed an engine that pushed the limits of physics almost as hard as the wing did. General Electric answered with the GE9X, the largest jet engine ever built for a commercial aircraft. Its fan diameter stretches 134 inches, wider than the fuselage of a Boeing 777. During testing in Ohio, it produced 134,300 pounds of thrust, a world record. But raw power wasn't the goal. Efficiency was. The GE9X runs with a 61-to-1 overall pressure ratio. Ceramic matrix composites allow it to operate at higher temperatures without heavier cooling systems. 16 massive composite fan blades move more air with fewer parts, and the result is about 10% better fuel efficiency than its predecessor. Combined with the new wing, the aircraft achieves roughly 12 to 13% lower fuel burn overall. that changes economics on ultra-long-haul routes. Small percentage improvements compound into millions of dollars saved per aircraft per year, thousands of metric tons of fuel avoided, thousands more in reduced CO airlines. Don't advertise that part, but they calculate it carefully. And while engineers were rewriting aerodynamic boundaries, passengers were quietly getting something else: a wider cabin, larger windows, higher humidity, lower cabin altitude, around 6,000 feet instead of the traditional 8,000. On a 15-hour flight, that difference is not theoretical. It's how exhausted you feel when you land. From the cockpit to the cabin, the aircraft borrows heavily from the 787 Dreamliner touchscreens, head-up displays, advanced diagnostics, even optional cameras that let passengers see wingtip-to-wingtip views on cabin screens. But here's the deeper question: was this innovation or necessity? The global aviation market has been shifting towards smaller, ultra-efficient twin jets for years. Point-to-point travel, flexible routing, lower risk per flight. The age of massive wide-bodies seemed to be fading. And yet Boeing doubled down. They built an aircraft that proves large wide-bodies can still compete if you bend the rules carefully enough. If you engineer around infrastructure, if you redesign wings, if you reinvent engines, nearly 500 airlines orders suggest the bet isn't irrational. But the story isn't finished, because folding wings solve a physical constraint, not a strategic one. The real test won't be whether the mechanism locks correctly. It won't be whether the engine hits efficiency targets. It won't even be about certification delays. It will be about demand. In a world chasing sustainability, decentralization, and smaller aircraft, does the future belong to bigger planes made smarter? Or did Boeing just create the most advanced bridge to an era that's already ending? And maybe the real breakthrough isn't that wings can fold. Maybe it's that the limits we think are permanent are sometimes just design choices waiting to be challenged. Because here's what most people miss: the folding wingtip wasn't just an engineering trick. It was a signal. For decades, aircraft size categories quietly dictated the shape of global travel. Airports were designed around them. Gates, taxi lanes, jet bridges, all calibrated to fit within strict wingspan codes. Step outside those invisible lines, and the ripple effects get expensive fast. So when Boeing stretched the 777X's wings beyond those limits, they weren't just redesigning an airplane, they were confronting infrastructure that hadn't changed in years. And infrastructure doesn't like being challenged. Airlines made it clear early on they would not order an aircraft that required airports to rebuild for it. No matter how efficient it was in the air, it had to behave on the ground. That constraint forced Boeing into a narrow corridor of possibility. The aircraft had to be physically larger and practically smaller at the same time. That contradiction shaped everything. But while the wingtip system grabbed headlines, another quiet shift was happening inside the numbers. The efficiency gains weren't coming from one breakthrough. They were compounding: 10% from engines, around 7% from the longer composite wings. Some of that offset by structural weight, but when you zoom out, the result is up to 20% lower fuel burn per seat compared to older models. On a 7,000 to 8,000 nautical mile route, that's not incremental, that's strategic. It determines which airline can profitably connect cities that previously didn't justify nonstop service. It influences ticket pricing, route planning, fleet decisions for the next 20 years. And this is where the story shifts, because the 777X didn't enter a vacuum. It entered a rivalry. Airbus had already positioned the A350-1000 as the efficient long-haul flagship. It didn't need folding wings. It didn't push wingspan boundaries the same way. Instead, it optimized within them. So Boeing's gamble wasn't just technical. It was competitive. The 777X had to prove that. Going bigger, but smarter, would beat going lighter and simpler. That's a difficult argument to win in aviation, especially after certification. Scrutiny intensified across the industry. The regulatory environment changed dramatically during the 777X's development cycle. Every novel feature faced deeper examination. The folding wing system, once just an engineering challenge, became a symbol of how much risk regulators were willing to tolerate. Testing expanded. Documentation grew. Delivery timelines slipped publicly. The message remained steady. The aircraft would enter service. Privately, every delay increased pressure. Airlines had fleet plans built around projected arrival dates. Competitors watched closely. And through all of this, one detail remained quietly unresolved. The future of large widebodies. For years, analysts predicted their decline. Smaller twin-engine aircraft promised flexibility. Routes could fragment. Instead of flying 400 passengers between megahubs, airlines could connect secondary cities directly. But long-haul travel didn't shrink. It evolved. Some routes consolidated. Others stretched further than ever. Ultra-long-haul flights exceeding 15 hours became more common. In those scenarios, seat-mile efficiency still matters sometimes more than flexibility, and this is where the 777X quietly makes its strongest argument. Not in raw size, but in cost per seat across extreme distance. The aircraft wasn't designed to dominate every route. It was designed to dominate the routes where scale still wins. Which brings us back to the beginning, the folding wingtip.